Okay, so I would like to give you a recap of the things that we saw on regression. And in particular, we saw two things based on regression, which are two methods, which are mostly the same. The linear regression, the least square method, so based on least square, and the mean square error. So what is the main object, the main goal of the regression? So we start by considering um, a system that we want to estimate. So imagine that you have an unknown system. Imagine that you have an unknown system with some kind of input and some kind of output. So do you don't know what is happening inside inside this system. So it can be anything that I don't know, any device, anything that can represent a transmission system. So you can have a lot of example of which is what is some kind of system. So you have your input data here, and you want to understand what is the output of this system. So basically you have something at the receiver, so at the other end, which is also corrupted by noise. So here you have some noise, and here you have your output. So you want to, based on the data you are putting inside this system, you want to estimate, you want to understand what is happening here in order to understand what is the process that transform your input in your output. So you have a correlation between input and output, and you want to understand what is happening here in the system, in the system that is unknown. So what is the basic things that you can do is to apply a regression model. So you put your input here. So what is this block? What is going? So you have any idea what is this block? So this is nothing but our function that we want to estimate. So we want to estimate the parameter that can represent this unknown system as much as possible. So here you have some output. And you need to compare so you need to compare this output, which I don't know is the estimation of y, with the real output according to any minimization problem. So based on this kind of process, you are going to estimate the parameter that, given an input, returns an output which is as much close as possible to the real output. So we want to estimate the error, so the difference here. Here you have the error, which is the difference between the real output and the estimated output. And this is this error can be generalized with the least square error or the mean square error methods that we saw. So based on this model, we can recognize two methods, which are the least square method. So we saw the least square method. What is about the least square method? The least square method, it is so we start from considering a training set. So our training set, which is based on our training set is based on a couple of input. So basically we have output and input. So we have output and input where basically we have some vector as input and a corresponding output to a vector. What we know about the training set for the least square method. So as you can remember, we know that uh, y and x are random variables. So as you can remember, we start saying that x is a random variable, so it can be drawn from some kind of distribution. And being x a random variable, of course, you have that also the output is a random variable, and you have some correlation between x and y. So y depends on x. So you have some kind of correlation between x and y. So we can say that you have some kind of correlation. And another thing that you can consider is the noise, which is another random variable. And it has an which is uncorrelated with respect to the input. So you have three random variables here, and you have that x and y are correlated each other because y uh, is derives from a transformation of the input, and you have another signal which is the noise, and this noise is uncorrelated with respect to x. So this is our model, and we want to estimate the parameters of this of our algorithms in order to understand what is the process that transform our input in an estimation of our output, of course. So we need to find the parameters of our model. So we want to derive the parameters here of our model in order to have this kind of minimization of the error between the real output and the estimated output. So first of all, we need to, as you remember, we need to choose a functional form. So the first thing is to So we need to choose a functional form, and this form can be, for example, linear or non-linear. So we talk about linear regression as we saw many examples. So we need to find some kind of linear dependence between the input and output. So the input and output are related by means of a linear correlation. What does it mean? That it is this system is a linear system, and just apply a linear transformation to the input. So it is rather easy to find a functional form of a linear. Of course, we have a line if we are in the two-dimensional space. So we have a hyperplane if we have in the three-dimensional space, and so on. So once we can define, otherwise we have a nonlinear functional form. So if our correlation is nonlinear between input and output, we need some kind of different forms. So for instance, the nonlinear, something like a polynomial regression that you will explore in directly in your homework, but it is not so different. So instead of having a line, you have something like a paraboloid or some quadratic forms of your output of the model. So, and you need to choose also a cost function that, in the case of least mean square error, you have your cost function, which can be written as the sum. So, so if you remember, we had this kind of situation in which you have a cost function, which is the sum of all the loss function based on all the samples of your input. So based on all the sample of your input, you find the const function that can be written in this way. So what is the next point that you must do is to minimize the const function. To minimize the const function, what does it mean? In this case, that you need to take the gradient of your cost function and put it to zero. So it is because the least square, if you remember, the least square is a convex function, so it is very easy to find the minimum of this function from the optimization problem. You just need to take the gradient. So you need to find the tangent to the uh, to your cost function and put it to zero. So when the tangent is zero, you are in a stationary point, and this point corresponds to the minimum of the function. So if you apply this kind of system to the least square cost function, you find that you have a solution. You need to solve this kind of equation. So here you don't have. Okay, too much. So you just don't have the k, the index k there. So it is very easy to solve the least square method because you need just to solve this kind of equation. And we saw a lot of experiments, a lot of examples, even in your homework, you find some example about least square method in which you need to solve this kind of equation. So on the other hand, we saw another method which is derived from the least square method, and it is called the mean square error method. What is the mean square error method? So you have more or less the same condition, but what happens in your training set? You have that your point x and y. So you have that. So you have that k and so you have that y and x. So your output and your input are random variables as in the previous case. But what is the difference between the uh, between the least square method is the fact that these random variables can change in time, for instance. So you can draw instant by instant a different sample, a different uh, batch of samples from your input. And this implies, of course, a change also in the output parameter. So they are random variables that can change in time, and this is more close to the real situation, so to real problems. Because imagine that you have your model, but of course your data are always different. So you want to generalize your model. You want that your model is robust to different kind of input data. Probably you are putting all the same kind of data, of course, but data are always different. So your model must be able to generalize some kind of input that changes in time, but it is drawn from the same distribution probability, for instance. So what is the implication of this kind of methods? Is that your parameters, which in this case are denoted by W in order to distinguish it from theta, in this case, your parameters are random variables too. So also your parameters may change in time. And this requires some kind of further operations with respect to the least square method. So as a first thing, you can choose the same scheme of the previous of the least square method. So as again, you must choose a functional form, and you must choose a const function, which in this case can be defined by the expectation of the squared error. So here you have the expectation of the squared error. So in this case, you just need to minimize this function. But the minimization follows the same process of the least square method. So you just need to take the gradient of your cost function and put it to 0, because the mean square error cost function is something like very close to the it has the same form of the least square cost function. But solving this cost function, this gradient, if you remember, leads to solve this equation, which is called the normal equation, in which you have that R is the expectation of the correlation of the input, and G is the cross correlation between input and output. So here you have matrix. So basically, you have this kind of things that we saw in the previous lesson. So as far as we have understood, we just need to have a clear idea of what we saw. So if you have any kind of things that you didn't catch, it is a good moment, because we go ahead and we move to different things to evolve these kind of things that we saw. So do you remember, you need to remember basically that the least square methods is based on a training set in which you have random variables as input and output, but they are just draw one time from their distribution, from the input distribution. You have a correlation between input and output. You have another signal, which is the noise, which is uncorrelated with respect to the input. You need to choose a functional form, which is linear or nonlinear. But in this case, we focused on the linear, and we choose the cost function, which is the least square cost function. We need to minimize this cost function and solve the resulting system, which is very easy to solve, of course. You have the same thing for the mean square error, but the different things is that your training set may change in time, and this implies a change also of the parameters that you want to estimate. So you need to minimize the cost function, which in this case is an expectation. So you are going to take the mean of all the things that you drawn in the input that you drawn from a distribution. So you are going to take the mean of the squared error. So you have the error between y and xwy, which is nothing but the estimation of x. So you have x and here y. So w, so you have the multiplication of x, the dot product between x and this the vector of the parameter, and you obtain the estimation of the output. So you take the squared error, you take the square of this error, and you take the mean, because you are considering multiple input. So you have multiple drones of your random variable. And in order to understand this problem, you just need to apply the normal equations, so which are based basically on which are the same things of this. So you have the expectation of this thing, and you have the expectation of this other product. So you have the expectation of the input correlation, and you have the expectation of the cross correlation between X and Y. So what does it mean? Just to remember to include the expectation here. I would like just to give you an overview of the possibilities of your of this kind of methods. So based on the possibilities of this kind of methods, we can apply this kind of very easy equations in order to find a solution, in order to find something that can model any kind of program like the ones we saw today. So, as we say, the mean square error is a fundamental topic. We saw, in particular, we focused on some kind of mean square error problems that can be seen as optimal linear filtering. So if you remember from the previous slides, I don't know if I have it here. So at the end of the lesson, we saw some kind of tasks related to the linear regression. One of these tasks is the filtering. So you have a dependence on the time instant, which is very important to understand this concept, because when you deal with signals, very often you are considering some time evolution. So very often you are considering some signal that is changing in time. And it is very important, because if you are considering something that a signal that is changing in time, you are considering a random variable that is changing in time. And if you are considering a random variable that is changing in time, you need to consider the mean square error regression, mean square error methods to solve your problem. And most of the signals that we will see in this course, that we will tackle in this course, are based on a time evolution. So if you consider any kind of I don't know, speech signals, audio signals, are always they are signals that show some kind of time evolution. Or I don't know, if you consider a time series, so you take some kind of data from your sensors, so you are considering a time evolution. You may not considering time evolution when you talk about images, if you talk about stationary images. But even in that case, you, as we will see, you can consider, for instance, some kind of things that we will see today. So you need to consider this kind of task, which is the filtering task. And in this kind of task, you can find a lot of problems, a lot of application, like system identification, interference cancellation, channel equalization, and so on. So we will see something like this kind of applications. We start from the basic one, which is the system identification. So it is a scheme which is very similar to the one that I draw. Of course, my drone is not so nice as this picture, But here we have an unknown system that we want to estimate. And here we have our model, which is nothing but our vector of parameters. So we need to estimate our parameters in order to provide uh, an output here, which is, in this case, it is directly represented as the mean square, as the error between the output and the estimated output. And here is the error signal. So based on this error signal, you are going to take an estimation, a new estimation of your linear filter. So the main goal of the system identification problem is to estimate the input response. So um, you need to find that your model must be estimated as much as possible closer to the unknown plant, so the unknown system that you are considering. So the error signal, so the error signal that you are considering is used in order to find the optimal parameter, because you are minimizing the squared error, and just minimizing this squared error, you are solving your the gradient of your cost function, which is based on the squared error on this signal. And based on this signal, you are deriving the parameters that you need to use. So you have your model here. You have the input. So we saw previously this kind of things. You can very often find this kind of notation in which with Y you denote the output of the plant, and with the letter D as the response, the overall response, which includes also some kind of additive noise. You can find this kind of system identification scheme in a lot of application. You can find it in controls, in I don't know, transmission channels, transmission problem, and so on. So based on this problem, you can apply the mean square error. So you just arrive to solve the normal equations, which are given, which can be written in this way. So you have the correlation, the correlation of the input, your vectors of parameters, and the output, which can be written in this way. What does it mean? So it means that your this means that since you are considering since you are considering a noise vector which is uncorrelated with respect to the input, you can see that the product between the expectation of the product between x and the noise signal is going to be zero, because if you remember, if you consider the mean value of two random variables which are uncorrelated, the product is zero. So what um, this kind of things is going to be approximated in this way. So you just consider the signal, the output of the noise, the output of the system without the noise. It is very important, this thing, because um, you can use the output signal, which is also corrupted by noise, but you can uh, consider it as it is a noiseless output of the plant, because we are considering an uncorrelation between the noise vector, the noise signal, and the input signal. So this assumption is very important because you can just take the response, the overall response of the system, included, which includes also the noise, and take this kind of, and you can apply the mean square error method. So in many practical systems, you can also have some kind of online version of system identification that we will see tomorrow. So tomorrow we are going to see what does it mean having an online learning and online algorithm. So it is just the very basic model that we can find. So you can imagine that you have any kind of problems like this one. So imagine that the unknown plant is, I don't know, your device which returns some kind of output transformation. It may be a communication channel. It may can be any kind of I don't know, some kind of electronic plant we can transform the input. So you want to estimate what does happen here, well, by just applying the mean square error. So just by applying the methods that I described before. One of the tasks of system identification, one of possible problems of system identification, for instance, is the echo cancellation. So imagine that you are in a video conferencing. So in this, I think that in these days you have a lot of video conferencing, video call with your friends, colleagues, and so on. So I think that it is more difficult because now all the devices are equipped with some echo canceller, but you may experience some kind of problems like echo cancellation. What does it mean having a echo cancellation? So imagine that you have your laptop, and here you have the loudspeaker of your the speaker of your laptop. So you find you have a far end signal. So the signal coming from in the far end, for instance, from your laptop, you hear my voice from your laptop. You have your my voice, which is a signal. So my signal is reproduced by the laptop, by the speaker of your output of your laptop, and the resulting signal, so it is a transformed signal, is going to cross an acoustic system, so an acoustic channel from your loudspeaker to the microphone of your system. So imagine that you have your laptop, you have your speaker, which is basically on the bottom of your laptop, and you have your microphone, which are close, for instance, to the webcam. So when the voice is coming out from your speaker, some kind of reflection of the input signal can be captured by the microphone and can be returned to the far end together with your voice. So imagine that you are talking with your friends. You have the voice of your friend that is reproduced from the loudspeaker and is captured also by your microphone together with your voice. So this signal, the sum of the signal from your speech and the speech of the far end, which is nothing but the echo, can be are captured by the microphone and are returned back to the far end user. But what is the result? That the far end user is listening to your voice, but also to a replica of his voice, his or her voice. So what is the goal of an echo canceller? Is to cancel this signal, so to remove this signal which is the echo. And so what, how does how can be applied this kind of echo cancellation? Just by considering the fact that the path that is the path that is run by the signal which comes out from the loudspeaker and is captured by the microphone is an acoustic path. So it can be modeled by a system. So it can be just modeled by a vector of parameters. So you have that this signal which is captured by the microphone is nothing but the input signal, so the X which is reproduced by the loudspeaker, which is convolved by an acoustic impulse response. So an acoustic impulse response is just a series of impulses, a series of impulses. So you want to estimate this kind of impulses, and you want to just by consider to build your model of parameters that is going to estimate this kind of acoustic impulse response, which is used to be convolved with your signal. Once you have your system of parameters, you have the multiplication, the convolution of the input by the, the vector of parameters, and you estimate the system, the signal, which is the echo signal, which is captured by your microphone. You are going to remove this estimated signal from the microphone signal, and you can return back the signal to the far end user. So uh, every nowadays every kind of um, software that we use, for instance, Skype or Meet or any other software that we can use, is equipped with this kind of model, which is a software model. So we are not going to think to any kind of the physical device which is installed on some laptop and so on. So it is very often some software algorithm that is going to process your signal. So it is very important that you understand this kind of applications, because you can find it anything that you use in your real in your daily life. So it is very easy to find this kind of applications, and you can have a view of the algorithms that we are going to study, because they can be used also to solve real problems. So in this case, you can apply also the some kind of mean square error methods. For instance, you can solve the normal equation even in this case in order to have the vectors of the parameters, and you can solve this problem. So you can here is the things that I said. One other task which is very similar to the system identification is the interference cancellation. So interference cancellation is a problem which um, is very close to system identification, but you have some kind of changes. So I would like to describe this thing just by looking at the scheme, the block scheme of the interference cancellation. So it is very similar to system identification, but we have some kind of things that changes. You have just one visual difference, which is the fact that the unknown system and the linear filter that you are considering are not taking the same input, but something that is slightly different. So it is very similar to system identification, but while system identification focuses on estimating the system inputs response, the uh, the goal of interference cancellation is to estimate the the output of your system, given the fact that you are not considering the same input. So you have access to this signal, which is the response that you are going to, which is available. This is the knowledge that is available, which is the sum of two signal, a signal y, which is the comes from the unknown system, and another signal which can be, for instance, some kind of useful signal, some kind of voice, some kind of anything that is that can be used. So you have the knowledge of this signal and the knowledge of x, which is nothing but um, something that is correlated with your output of your system. So you have that, of course, again, you have a correlation, a statistical correlation between x, the input, and the output. So the task is to estimate the signal y and remove it from the response that you are known. So it is very close to the previous problem, but in this case you have this knowledge, the knowledge of the response, but you don't have the real knowledge of the signal that is going uh, to be fed into the unknown system. So what are some assumption is that there's the desired signal of course contain um, uh, this kind of signal which are statistically independent as in the previous case. So you can consider, if you consider the normal equation, you can consider that the cross correlation of the signal, the response is can be approximated by the mean value of the multiplication between the input and the output, because as I said previously, if you take this multiplication, you have zero as output, because you have that x is independent of this signal s, and which is the same assumption that we saw from the previous example. So it is something that we have said. So we can have a lot of application that implements this kind of scheme. In order to understand better this problem, I would like to have a description of a real life problem like the echo cancellation. In this case, we have the noise cancellation. So the name is very close to echo cancellation, but we have a very sensitive difference, which lies in the scheme that we are going to consider. So we do not consider the same input as for the echo cancellation. So here you have the unknown system and your system to be modeled, and you have the same input. In this case, you don't have the same input. So I would like to give you a real example in order to understand this kind of problem. I would like to describe this problem just by showing the scheme, which is more easy to understand. So, noise cancellation is a problem of interference cancellation. So, you have a target signal D, which is this signal which is collected by a sensor. For instance, we can consider the example of the cockpit of an aircraft. So imagine an aircraft cockpit in which you have the pilot inside. You have some kind of microphone which is close to the mouth of the pilot, and the pilot is speaking. So the speech signal of the pilot can be represented by the signal S. So this sensor is nothing but the microphone which is close to the mouth of the pilot, which is inside the cockpit. But you can so this microphone also capture the aircraft noise. So imagine that you have the noise of the aircraft. This kind of noise is also captured by the microphone, and you want to remove this microphone, but you don't have a reference for this kind of signal, as it happens for the echo cancellation, because the input is arise to your laptop and you can use it as a reference. So in this case, you don't have any kind of reference, but you know that you know what is the noise source, which is the aircraft. So the movement, all the motor of your aircraft and so on. So all the noise that is generated by the aircraft. So you can exploit the noise source, and you can put another sensor, for instance, outside of the aircraft in order to capture only the microphone. So you have a different signal between the signal that is captured by the microphone inside the cockpit, but you can you know that both the noise signals, are drawn from the same distribution. So they both come from the same noise source. So you can use this kind of signal in order to estimate this kind of noise signal which is captured by the microphone signal. So you want to exploit this signal B2, and you can transform it by a noise canceller in order to estimate V1. So the same signal, so you have a statistical correlation between these two signals because they are drawn from the same distribution. But uh, based on this signal, you want to transform it in an estimation of V1, so to remove this estimation from the microphone signal. And in this case, you can remove the noise from the microphone, and here the speech signal from the pilot is transmitted without any noise to a far end user, through, I don't know, the ground control, I don't know, something like this. So it is very significant because it is another problem that can be found in lots um, of things that you are considering. For instance, imagine that you have your headphone with your noise cancellation. So they are all based on this kind of schemes, on this kind of approaches. So for me, it is very important that you understand very well this kind of problems, because you can build algorithms in order to solve real problems. And I think that is a very cool thing, because you can approach to very actual, very nice problem and solve it just by applying the algorithms that we see in this course. So I will tomorrow. I will show you an example of how to deal with this kind of problem. So we will have an exercitation, an exercise, a lab session on this kind of application on noise cancellation, in which we have a mean square. We use a mean square error method in order to solve this problem. So we take this kind of assumption, but we basically move also to more real cases, as we will see tomorrow. So at the end of the lesson today, I will send you uh, um, a notebook, which is a void notebook that we use tomorrow, in which you have some text of the problem that we will see tomorrow. So in this case, you can try by yourself to fill that notebook. I don't know, this afternoon, if you have time. So tomorrow I just give you some explanation about how to solve. I will give you the correct version, the correct algorithms to solve your problem. So it is based on the equation that you can find here. So you are so in the example that we saw, we are considering two signals coming from the same noise source, which is considered as an autoregressive process of the first order. I will give you also some kind of additional material in which you can find some notions about what is an autoregressive process and what are the main properties of this kind of processes. But just to give you something which is additional to what we see in this course, and I will put it as an appendix. So if we have this kind of noise signal, noise process, you have some good um, properties related to the autocorrelation matrix, which is very easy to find. So you just considering the variance of the signal that you are considering. I will give you all the additional material from which you can arrive to these equations. But you just need to know that if you have some signals that is drawn from this kind of process, the autocorrelation coefficients can be easily derived in this way just by using the variance of the signal. So you need to build the matrix of the autocorrelation matrix, and you need to compute the cross correlation vector. So here is I will explain all the passages tomorrow, but here you compute you have two elements in this case. You compute the first element and the second element, so they are both based on the variance of the noise, and you just solve the normal equation just by having the matrix or the autocorrelation matrix and the cross correlation vector, so you can derive the vectors of the vector of your parameters. Here is the text and the problems that we will see tomorrow. So given a noisy signal, so a signal that is captured by the microphone here. So given a noisy signal, you can find you have the output, the error signal, which is a denoised signal from the correlated source, and you will see that how this signal can change if you vary um, the correlation between the noise signal. So as much these signals are correlated, and as better is the estimation of the noise signal B1 from B2. We will see tomorrow this kind of example. I will give you the notebook so you can find some equation, you can find some text. So tomorrow you can write directly on that notebook. So I can explain you quickly. So, and you can have also some kind of additional material in order to better understand your lab session. Another thing that I want to say, so we start just by giving you this example in which you need to estimate, you need to solve the normal equation, but tomorrow we will also we also go ahead with the theory, and we will see um, some advanced things in order to estimate the parameters of the vector in cases in which you don't have some easy signal like a sine or a sinusoid, but you have some kind of real signal drawn from real microphones, for instance. But tomorrow we will start just by looking at how to solve problem of noise cancellation. I would like just to briefly give you some information about other kind of tasks of mean square error application, which is, for instance, the inverse inverse system identification, or also known as the convolution. So we saw previously that in the cancellation task, so we want to remove the output of the unknown system. So we want to estimate a signal, which is an estimation of the output, and we want to remove this kind of signal from a response, an overall response, which is something that you want to preserve, and you want to preserve some that contains some useful information that you want to preserve. So you want to remove anything that is not useful for your end user. So in system identification, the focus on the unknown system itself. So you have two different tasks, but related to the system and to the output of the system. In inverse system identification, instead, we want to focus on the input of the system. So our goal is to recover the input of our system as a delayed version of we want to estimate uh, our input in a form of a delayed version of the signal itself. So this kind of task is known as channel equalization, or just known by equalization in a lot of problems of, for instance, communication problems. But it is also known as deconvolution in problems like image deblurring. So we given an example. We gave an example of image deblurring at the beginning of this course. So in the convolution, you want to have an approximation of the input. And in channel equalization, your estimation is approached by a transmission of a training sequence. So, for instance, if you consider an equalizer, the goal of the equalizer is to recover the transmitted information, uh, considering also the noise that you can find at the receiver. So we can look at the scheme. which is easier to be uh, to be explained. So imagine that you have a transmitter here, but you can consider this kind of system related to a lot of problems. So here it is very easy to think to a communication system, but of course you can think to any kind of problems that have something like a transmission and a receiver, a transmitter and a receiver. So you have a transmitter that transmits some signal. This signal uh, is fed through a channel. This channel applies some kind of transformation to the signal at the end of the channel, so at the receiver you have some kind of noise, which is some local noise due to the, I don't know, thermical noise, rather than some kind of noise from the device, from the channel, or some background noise. So it depends on the application that you are considering, but you always have some kind of noise at the receiver. So you have this kind of a signal X, which is a transformation of the transmitted signal. So the signal X in this case is the input of your equalizer. So what is the equalizer in this case? Is nothing but an inverse transformation of this channel. So you want to draw something that take the same transformation of that is performed by the channel, but in an inverse way. So in this way, you want to apply an inverse transformation in order to to remove, to delete any effect that is due to this, to the transformation applied by this channel. So in order to apply an inverse transformation here, you are considering just plain transmission here. So you are not considering any kind of transformation. So you want uh, to avoid any kind of effect given by the transformation from this channel. So you have a transformation here, an inverse transformation here, in order to have the same at the output, the same signal. You are not the same, you have not the same signal actually, but you have a delayed version of the input, because your signal is going to be processed by a channel and to be processed by an equalizer. So you have some kind of time that is taken to, in order to perform this kind of operation. So at the receiver here, you have a delayed version of your transmission signal. And you can find these kind of schemes in a lot of equalizer, but they are equalizer, but you can consider also not only channel equalizer, but other kind of equalizer that you can find in every kind of application that you are also studied in your engineering path. So you can think to a lot of engineering application that can be represented by this block scheme. And so here is a numerical example. If you want, you can try to perform it. And just to conclude, I would like to give you some kind of other kind of example of inverse system identification, which is known as deconvolution. And it is applied to images and it is known by image deblurring. So we saw this kind of example some lessons ago. So you have an original image and the same image which is blurred. So imagine that you are taking a photo to any kind of, to a boat or any kind of things that you want, and you are moving. So if you move when you take a photo, you have a blurred image. But now we have a lot of artificial intelligence software that is going to deblur the image while you are saving your photo in your gallery. So when you look at when you hear to the camera with artificial intelligence, so it's nothing but algorithms like this one, which are correcting which is correcting all the problems that you can have. For instance, if you move when you take a photo, an image deblurring algorithm is applied in order to recover the um the non blurred version of the of the image. So the convolution is a typical problem. It's a process that is very related to the human brain. So it's a process that our human brain performs when you look at something, because the vision system of a human is like something very complex. And the image that falls on the retina of your eyes is something that is very blurred. So on the retina of your eyes, you have impressed an image which is very blurred, and the blurring system in this case is your brain. So your brain is continuously taking this kind of operation, which deblurs the image that is impressed on your retina. So it is something that is very strange, but it is true. So you have this kind of algorithms that is performed by your brain. So we are not so surprising when we talk about artificial intelligence and so on, because our brain is capable of lots of tasks that are very complex, and it is in an automatic way, because we are applying our vision in every way, in everything that we see. So here we have an infinite extent, because we are considering a wide sense stationary. We are considering an image which is stationary, and we can put it on an infinite extent. So we have causality of your system. So we can solve the normal equation in the frequency domain. So since you don't have a random variable that is changing in time, you can consider an infinite extent by just transforming the image in the frequency domain. So in the frequency domain, you can have a two-dimensional array, and you can solve directly the normal equation in the frequency domain, just by applying the Fourier transform of the signals that we have. And this is the scheme of the deblurring. So you have your the picture that you are going to photograph by your camera. You have the snapshot from your camera, and you have the shot from your camera, and you have a blurred image. So you apply a deblurring filter here, and you have an estimation of the picture that you are going to actually see. And it's something that is very interesting, because you can also find a very complex deep learning algorithms that is going to be applied to the blurring scheme of the inverse system identification, just by involving some kind of more sophisticated deblurring image, in order the blurring systems, in order to recover the original signal from a noisy one or a blurred one. So we will also talk about image deblurring more in the last part of the course, when we will see some kind of deep learning architectures in which we can apply this kind of things. But it is very important to understand what are the approaches behind this kind of application. So you can apply very easy schemes, or you can apply also very complex models like deep learning that we will see at the end of the course. That's 1 minute to give you an explanation of another case, which is the beamforming. So the beamforming is something that is can be applied by using an array of sensors. So imagine that here you can have an array of sensors, which can be, for instance, antennas, or they can be microphones, and you want to use this kind of microphones of sensors in order to look at a specific direction. So you combine all the signals captured by these sensors in order to electronically steers the vectors of your to a desired source. So imagine that you have a source that can change in space. You can use some kind of sensors in order to point towards a direction. So instead of moving the sensors toward that direction, you combine the signals collected by these sensors in order to electronically steers the beam, the main beam towards a desired direction. And in the same case, you can remove any kind of noise, any kind of interfering sources coming from other directions. So it is a very nice application that we can also take some kind of problems. Probably, if you are interested in, you can see something like this one, probably in a project, I think. But you can imagine, for instance, to home devices like Amazon Echo, or I don't know, Alexa, and something like this one. So if you look at that kind of devices, you have some kind of microphone array in which you can also that is able to understand what is the direction of arrival of your source, of your speech, signal. So if you are taking some commands to your home devices, you are taking some voice, but you can be any place of you around your home devices. So you are in your room, but the device does not have precise knowledge about your position. So based on array of microphone, it is capable of determining the localization of your point. And based on a beamforming system, it is capable of electronically pointing towards the location in which you are. So in that case, uh, it combines all the signals that is collected by the array of microphones that it's capable uh, to collect the source signal coming from your position, also reducing any kind of interfering signal coming from the other direction. So it is also a very interesting application, and it can be also solved by applying mean square error, mean square error signal, mean square error methods. I thought in this case you have some constraint to be considered. So instead of having a minimization of the mean square error, like the problems that we saw, we have also a constraint in this case, but it is very easy to be solved. So I would like to stop here, stop this lesson here.